All right, so about existence and uniqueness. Suppose you have some kind of x range, like AB. X's live in here somewhere. So there's like an x naught point. And then, let's see, you have also some initial condition that's determining things, right? So that's your kind of y of x naught is y naught condition. And then you have something about the slopes of your function y. Right? So suppose just for instance that what we know is we know that f of x and y is a continuous function.
So right there, does that mean that everywhere on that rectangle?
Yeah, that means that everywhere on that rectangle, f of x and y is a continuous function.
Like there's a curve everywhere on that? Like can you like pick a point and be like, oh, this is associated with the curve and I can get a derivative and a y prime right here?
Yeah. How about if I plugged in any particular point in this rectangle, not only would I get an output from f, but also if I vary the point that I'm plugging in a little bit, my outcome from f would be similar, right? Like it would vary continuously. So a little change in this area begats a little change in your function f, and your function f is directly tied to what your derivative information is going to be.
So starting out, we kind of have like infinitely many curves that saturate this thing, right?
So starting out, what we have is kind of the idea of a direction field, and the direction field varies continuously.
Okay.
Right? Like really, you might think about this as kind of dy dx, right? So there's some slope information associated to each and every point in your rectangle. So that might look like this. Right? But whatever's going on, they vary continuously, right? That's this assumption that f of x is continuous. You guys with me on that? So everywhere around, you've got some little slopes, and they kind of change in reasonable ways. Then what our existence part of the existence and uniqueness theorem we've got says is that there is, at the point x naught, let me move my x naught over so it's in the middle of my little cloud of stuff, and y naught, right? Like, if I give you an x naught and a y naught, you can solve, well, and this is the sticking point. There is a solution. That does not mean that you could solve it. Does that make sense? Like, you might not have the tools, but there is at the very least at least one solution, right? So there might be, so here's a little dot here. There might be some solution that does something like this. Like that seems like it matches up with the slope field that I've got, right? So at least on some little interval here, there's a solution that works. You guys all good with that?
Just like it could be like a really, really, really tiny baby one, or is it the whole slice?
It's not necessarily the whole thing. It's just on sub-interval of this rectangle. But there is at least a solution that works for a little while. It's likely that it works for the whole rectangle, but it's not a, there's some sticking there. We'll talk about more where those sticking points occur as we kind of move on. When we get to the series part of the class, we'll have a like really nice idea of where those sticking points occur. But for right now, it's just like, yeah, on some little interval at least, I can get this solution to work. It might be that one. You with me on that? And it's in an x interval. It's not a y interval. It's just in that. You guys with me? Why is it only in the x that matters?
Because y is a function of x?
Yeah, because y is a function of x. Like once you know where you are, you should be able to flow forward or backwards along that. And you're not going to get maybe some interval in y's because x naught might be the maximum of that kind of function. You guys with me on this? So far this is one solution. Now the thing about the existence part of the existence and uniqueness is that I don't know that there aren't two. So there might be a case like this. And you guys will note I had to do something a little wacky there, right? Like I had my slope fields, and this thing doesn't look like it flows along the slope fields, right? What's the reason for that?
Because where they meet, like the slope has to match.
Yeah, so they have to be tangent right here. You guys see that? And if they're tangent right there, then it feels in my head like, well, couldn't you just like go a little tiny bit along that tangent line and then figure out where you're at and then evaluate the slope field there and figure out where you have to go and then go a little bit along that? Like, does that kind of make that idea make sense at least?
Yeah.
Yeah, so the thing is that in your head, you're assuming that the derivative's continuous. Because it makes sense that the derivative would be continuous, the y partial. In other words, the slopes would vary in a continuous way as I went up and down. Yeah, they might not. But if I kind of have in my head that they do, then I know that solution has to be unique. So this case where you've got the yellow and the pink, or the orange and the pink, that can only happen if your y partial of your function f isn't continuous.
So that would be like, at that point, if you went a little tiny bit, if you're looking to the right, you would have like two derivatives sort of or something, or?
Or like if I went a little tiny bit to the right and then went up or down, the slope information might be drastically different.
Okay.
You can see that? Like the idea of this slope field could have a kind of a discontinuity. It's not actually a discontinuity because it's just a discontinuity of the derivative, right? So there could be a cusp in the way the slope fields change. Does that kind of make sense? Like it could be any little bit you are on this side of your tangent line, the slope fields are all kind of negative. And on that side, they're all positive. They might meet in the middle in a reasonable way, but the slopes, the rate of change of the slopes is annoying. You guys with me on that? Think like looking at an absolute value function for your slopes.
So you just like hit a point and then it just totally different direction, sort of.
Yeah, so like the rate of change of your slopes as you go this way might be 1. The rate of change of your slopes as you go that way might be -1. But they're both 0 in the middle. That's not quite what I have here, but it's close. You guys sort of see that? That would preclude you from doing that like, well, I'll just run out along the derivative a little bit, right? Because run out along the derivative a little bit is not the same as actually going along the function curve. Right? Like you're trying to kind of step out of the way with a secant line. You guys see that thought? So like here's your dot. Here's your tangent line, right? Blown up. Now, if the orange one goes like this, and the pink one goes like that, right? Your idea of like, well, I'll just walk out along the tangent line a little bit doesn't give you a good approximation. You guys see that? So this is the kind of thing that could go wrong that would have two solutions. That said, the y partial of f's probably continuous most of the time, right? That's not actually true. That's totally a lie. If you pull a function out of a barrel, its y partial is discontinuous. But if you pull a function out of a barrel, it's discontinuous. Like if you just make a random function. So a random function is just an association, in this case, between R2 and R. Right? If you make a random way to do that, it's going to be full of holes. Because there's only one way to agree, but there's a lot of ways not to agree. You guys with me on that? What book is that from? No? Quiz? Russian literature?
Ask him. He wasn't listening.
Damn it, Jordan.
Is it War and Peace?
I believe the book starts, every good family is the same.
All families are unhappy in their own way.
Yes. Every happy family is the same. Every unhappy family is unhappy in their own way. Because there's only one way for a family to be happy. Everything has to work.
So this applies to functions of, or families of functions as well?
Yes. So the idea with a function, right, is for a function to be continuous, everything has to work perfectly. But there are way more ways to be broken, right, than there are to work.
And by the way, that's not from War and Peace. That's Anna Karenina.
Yes, it's Anna Karenina. Cool? Yes?